Hey guys, Mr. Palmer back with part 3 of our physics review here on work power and simple machines. These two problems are going to involve the real work equation where we have an angle. These are numbers 5 and 6 on your review sheet. Hopefully you've tried them, then you can come back and see my explanation. We have a 250 kilogram boulder that's being dragged 19 meters across level ground. The rope, however, is making a 34-degree angle with the horizontal. It tells us a 500 Newton applied force and 275 Newtons of friction, and we want to find the total work from all of these forces. So obviously, I've already placed for you the work equation that's over here. We have a free body diagram that I've already started. So if we have our object, which is, 250 kilograms, it's being dragged 19 meters. So I'm just putting in here this dashed line to the right. That's the distance it's going, 19 meters. The applied force is 500 newtons, and it's making an angle of 34 degrees with the horizontal. Friction is always opposite the direction of motion, so you'll see that I've shown friction on the left-hand side. Here's our force of friction, and the force of friction is 275 newtons. We're going to calculate the work. We can look at two other quantities of work, the normal force and gravity. But what we already know, if the object is going to the right, it's being dragged 19 meters at constant velocity, the work from this is going to be 0. The work from the normal force is going to be 0. But friction and our applied force are not. So let's look at our equation and see if we can calculate this. We're told that this is 500. Let's use our real work equation to find the work done by the applied force. So work from the applied force is equal to the force, which is 500, times the distance it's being pulled, which is 19, times the cosine of theta. Our angle happens to be 34 degrees. Plug that into your calculator, making sure that you have your calculator set for degrees and not radians, is going to give you 7,876 joules. Now we also need the work done by friction. So friction is always going to be doing negative work. It's going to be slowing objects down. It's going to be stealing energy out of our system. So let's do the work from friction. The work from friction, well, we know that the force is 275. If we look at the distance, well, what is the distance? The object is moving 19, but friction is pulling in the opposite direction. So how does that affect our problem? Well, if we look at the cosine of theta, the angle that the frictional force is making is actually 180 degrees. The cosine of 180 degrees is -1. So what this really does is if an object is pulling in the opposite direction that it's moving, we can really just call this a negative work, right? We don't have to really fiddle around with calculating some angle because the cosine of 180 we know is -1. So if we multiply this out, it's going to give us negative 5,225 joules for the work that's being done by friction. 7,876 is the work being done by the applied force, and we're going to add them together. The work total is going to be the work from the applied plus the work from friction. So if I'm adding together positive 7,876 and negative 5,225, that's going to leave us with an overall 2,651 joules of total work. And if we look up at the question, it says, what does your answer tell you about the speed of the boulder? Well, the speed of the boulder is going to be increasing because this is going to be positive work. We've put energy in. It must now be going faster. We have accelerated the object. Okay, let's look at a slightly different problem. This is one where we're going to be pushing an object up a box, a box up a ramp. It tells us that the length of the ramp is 5 meters. So if I'm going to go into my problem, I've already made myself a little diagram. This is going to be 5 meters. It tells us that it's making an angle kind of shallow. This is a 25-degree angle in here with the horizontal. The mass of our object is 50 kilograms, and it says that we're going to be applying the work that's going to be done by our applied force is 850 joules. So the work from our applied force is 850 joules. So what's it asking for? First, find the applied force, and second, find the work that's done by the weight. Okay, so let's start by looking at the work done by our applied force. Right? That's going to be our applied force times the distance that we are going to push it. Well, our applied force is going up the ramp. The ramp is 5 meters long, so we know the distance is going to be 5. We're going to multiply that by our applied force, which we don't know what it is. But we do know that the work is 850 joules. So we could put that in and solve for the applied force. That gives us a force of 170 newtons. Well, what is the work done by the weight? This is a little bit trickier. What's really happening here? This object is being raised up the ramp. So let's look. The weight is pushing down, right? The weight is pushing down, and the object, when it gets to the top, is now higher, so it is now some distance above where it started. And we have to look at the distance in the y direction, the direction that gravity is pulling us. So again, we want to do the work equation. Work is going to be force times distance, but now it's the force of gravity and the distance against which gravity is pulling. So what distance is it raised? Well, that's going to make us have to figure out what this height of our ramp is over here. So our work is going to be really equal to the force of friction, which is mg, times the height of our ramp. And because you guys know trigonometry, if I have the angle here and I know my hypotenuse is 5, the sine of 25, right, is going to give me the opposite, which is my height, over 5, which is my hypotenuse. Right? We usually call this the x or the y side. So if we do that and we solve, that's going to give us a height of 2.11 meters. So that's going to go into our equation. We're going to put in the mass, which is 50, times 9.8, times the height that it's going to be lifted, which is 2.11. Multiply that together, we wind up getting 1,035 joules. Why does it happen to be negative? Well, it's going to be negative because we are applying the force down, but the object is being moved up, so it is opposite that. So the work comes out to be negative 1,035 joules. All right, guys, next we're back with some simple machines.